Hey gang, Terry here, and in this video we're going to really conceptualize the first law of thermodynamics by going through a few different scenarios, and we're going to use this really cool applet that's available online to help guide our way. And if you want to check out this applet, the link's in the description. It's totally free to use. So let's begin. Now, number one, write the first law mathematically. Now, there are many different ways to express the first law, but we'll just write it in this form here. So the change in internal energy of the system equals the energy transferred as heat to the system plus the work performed on the system. Now, number two, what changes occur if the work performed on the system is greater than 0 and the energy transferred as heat equals 0? Well, let's do this with this applet. So we'll make the work greater than 0 here. When we have positive work, that means the surroundings is performing work on the system. We have 10 joules being performed on the system, and we're transferring this energy on the system by compressing this. And imagine there's a gas in here. We're compressing this gas, and this compression causes a transfer of 10 joules of energy into it. Now, we'll assume these walls won't allow any energy to leave as heat, so they're adiabatic walls. And since we're putting 10 joules of energy into it, the system, none of that energy is leaving, so the internal energy of the system is increasing by 10 joules as well. And we can play it here. See, it's being compressed. The temperature is going up, and the temperature is going up because the internal energy is going up. There's nowhere else for this energy to go. It can't leave as heat because we're assuming this heat transfer is 0, so we're increasing the internal energy here. Okay. So we'll reset that. And scenario number 2. So write the first law. Again, there's many different forms, but we'll stick with this form here. Change in internal energy equals the energy transferred as heat plus the energy transferred to the system as work. Now, what changes occur if Q equals negative W? So the energy transferred as heat equals the energy transferred as work, the negative of it. And also, the work is less than 0. So let's make the work less than 0, negative 10. And we'll make the heat here 2, or 10, plus 10. So these are equal and opposite, just like what we require here. And we have the work less than 0. So in order for, if Q is positive, that means 10 joules of energy is being transferred into the system. The system is gaining 10 joules of energy by heating it up. We're heating it up, so 10 joules of energy from the fire is going into the system here. Now, at the same time, the system is losing 10 joules of energy as work. The system is performing work on the surroundings. The system's performing work, and it takes energy to do work, to push against the surroundings. So when the system pushes against the surroundings in order to expand, it loses energy. And the energy gained as heat is equal to the energy lost as work. Therefore, there's no net change in energy for the system. So the change in internal energy is going to be 0. So this temperature is not going to change. It's going to remain 300 Kelvin. This will be an isothermal expansion. So if we press play, this is heating it up, but at the same time, that extra energy that's coming in as heat is being used as work to expand the gas here. So that's cool. Next one here, what if Q equals negative W, just like what we have here, but the work is greater than 0? So we'll switch this around here. And the work is greater than 0. That means work is being performed on the system. The system is gaining 10 joules of energy from the surroundings. And the system is losing 10 joules of energy as heat. So we have these ice blocks here to indicate that energy is being transferred as heat from the hotter system into these colder surroundings here. The system is losing 10 joules of energy as heat. But at the same time, we're pumping 10 joules of energy into it by compressing it. We're transferring energy into the system in the form of work. And at the same time, that 10 joules of energy being transferred into it is being lost as heat. Same thing, the temperature won't change. It'll be an isothermal process. Right on, cool beans. Okay, last scenario, write the first law, so we'll write it out again. delta U. There's different ways again, but we're sticking to this way. Change in internal energy equals the heat plus the work done on the system. What changes occur if work is less than 0 and the heat is less than 0? So in this scenario here, the system is losing energy in the form of heat. So we have energy being transferred as heat away into these ice cubes here. It's losing energy from heat. And it's also losing energy from work as well. So this system is performing work on the surroundings while it cools down. So it's losing internal energy from energy as heat, and it's also losing internal energy because it's performing work on the surroundings. So the total change in internal energy is equal to the energy lost in form of heat and from work as well. And if we play this, it's getting colder, and it's getting colder at a relatively fast rate because it's losing energy both ways here. All right, that's it. Hope you enjoyed it. If it was beneficial, please give it a like, and I'll see you in the next video. Cheers.